Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good afternoon, everyone. It's my great pleasure to welcome Renan Vital, who is visiting us this week from the Hebrew University of Jerusalem. Renan actually got his PhD from Hebrew University in 2006, and then he did a postdoc at Berkeley, and he's been faculty there since 2008. He's a longtime collaborator of some of us here. We had co-authored a paper on edge-preserving decompositions in 2008, and he's also been a collaborator of Johannes Kopf. And he's going to tell us today about Blur-Kernel estimation.
Thank you, Rick. Thank you for inviting me to MSR and to give this talk. So I'll be talking about deblurring. To work with Amit Goldstein. Used to be a PhD student of mine. He left to the industry right in the middle. Okay, so as we all know, in many practical scenarios, we hold the camera either on our hand or it's on some moving vehicle. We can't fixate it, and the exposure time is not zero. So the camera sees the motion, integrates it, and the resulting image is blurry, which is something that we don't like. Details are missing and so on. So deblurring is all about removing this blur. So the typical model that people have been used is the following. So it's the blurry image B is the convolution of the unblurred image, the sharp image, and some blur kernel that basically tells how long the camera was exposed at different offset that were integrated, plus some pixel-independent noise term eta of x. Recently, people have started asking, what's the scope of this model? Is this an accurate model? Does this model explains every blur that we may see? So the answer is no. It is valid for small rotations in the camera along the x and y directions. It's not valid when there's motion in the camera, because if there's motion in the camera, then we might see parallax effects, occlusions. And also it's not valid for the cases where we have rotation of the camera along the optical axis. But I think that when people hold their camera in their hand, these are the two most significant angles that do go into account, but then again. There are two classic categories of image deblurring: the non-blind deconvolution. We know the blur kernel. We measured it somehow. We have it somehow. And all we have to do, and it's not a simple task, is to deconvolve the blurry image with the blur kernel. And it's not a trivial task simply because there's noise, and the model is not always perfectly accurate. Blind image deconvolution says that we don't have the blur kernel as well, and we have to recover both the blur kernel and the sharp image. So now we have this problem of underdetermined problem. There are more unknowns than equations. This work, and actually a few others that I will mention, kind of open a different category where they do not fall to either. So we're estimating the blur kernel. We don't have it. Nevertheless, we are not recovering the sharp image in the process. So it's not a part of the algorithm. So we get the blur kernel out of this new algorithm, and now we need some non-blind deblurring in order to produce the final image. So image deblurring, I think it's one of the most researched problems in image processing. There have been tons of work. So I think the most dominant approach is the map approach, where the formation model of the blurring image is transformed using the Bayes law into the physical model times some Pio model over the latent sharp image and the blur kernel. People the first attempts, the people used Gaussian models for the images or their derivatives. Later on, people started using the total variation PIO, the L1. More recently, the map K, where there's an integration across all the possible images. So people compute the marginal distribution across all the possible images, and they optimize for the kernel in an independent manner. This requires major integrations. I mean, integrations at a very high dimensional space. Dilip and Rob developed an alternative, a normalized metric that tackles one of the problems that were originally in the map-XK approach, and there was another acceleration of the map-K approach. A different type of methods make an explicit use of the fact that there are sharp edges in the original image and try to recover the blur by the deviation of the edges that we see in the input blurry image. So Neil has a work using the two-color model to explain sharp edges. Jointly recover an image that behaves like a sharp image using some inverse diffusion process, and then try to see what's the difference between this sharpened image and the input image, which is supposed to be the Blur-Kernel. Chert al. Do something quite similar. They detect edges, and they look at their profile, and they use a Radon transform to recover the profile itself. There are works that try to employ hardware into the process, different ways of playing with the shutter in order to generate some sharpness into the Blur-Kernel. In the time integration, the coded aperture of a Nat-Levin that allows better spectral behavior, and also the recovery of the scale of the blur, and the acquisition of parameters basically that generate the Blur-Kernel, the motion, the rotation, in another work of Neil. And then there are new methods that try to incorporate the more detailed model that does not only account for translation type of blurring, but also for the rotation. These are relatively new works. They typically use the map formulation to recover the three-dimensional Blur-Kernel once you add the additional rotation. So this work kind of goes into a different path, and the motivation, I think, comes from the simple visual observation on blurry images, that blurry image is in fact a superposition of a sharp image just moved around. So the image kind of resembles itself at various offsets because it's a sum of the same signal just translated. And then the question is, how do we formalize that and see what are the similarities inside the image which would indicate the blur? So some theory. There is a well-known power law that people use to describe the fall-off of the power spectrum of natural images. Here it is. They are supposed to decay something around like the frequency to the power of 2. So if we believe in this model, we could do the following, take the following approach. We could take the Laplacian filter, for example, the 5-point Laplacian filter, and compute a filter which is the square root of that filter, meaning that D is a filter such that if I would convolve D with itself, I would obtain a Laplacian filter. There are actually many such separations, but there's only one that is symmetric. And since L is symmetric, such a decomposition should exist. So D is a filter that if I would convolve it with itself, I would obtain the usual 5-point Laplacian or any other type of Laplacian. So let's see what we can do with such filter. So if I would convolve the image with this filter and look at the power spectrum of this signal, So in Fourier space, we have the convolution theorem that separates it into the image times the differentiation filter squared. The differentiation filter squared is actually the Laplacian. It has the same spectral response as the Laplacian, and we know that Laplacians behave like omega squared. Every differentiation adds multiplication in Fourier space by omega, meaning that this filter actually whitens the spectrum of the image. Okay? So, in case of a blurry image, we could just convolve with this whitening filter and get this identity. I think there's missing one absolute value part here. And we know that those two cancel one another, so we are, I'm sorry, this one cancels this one, so we remain with the power spectrum of the Blur-Kernel, which is like halfway, right? We want to know the Blur-Kernel. Here is its power spectrum. We are missing the phase, so we could use some phase recovery method. There's quite a few of them. So this is the general direction that we would follow, except that there are some complications that we'll have to deal with before. So another useful identity that we will have to use is the Wiener-Khinchin theorem that relates the autocorrelation or the Fourier transform of the autocorrelation of a function with the absolute value, with the power spectrum of that signal. Okay, so autocorrelation is actually the convolution of the signal with a mirrored vision of itself, which is in Fourier space, a pointwise multiplication between the signal and its conjugate. So we get the absolute value in Fourier space. It's a very useful relation. So this relation basically introduces a spatial counterpart to what we've seen before, right? If we know that in Fourier space we're expecting to get a white spectrum for the image convolved without whitening filter, that would mean that the autocorrelation of the image in real space convolved with that filter is supposed to give us the delta function. And similarly, if we're looking at the blurry image, which gave the power spectrum of the Blur-Kernel, now we're supposed to obtain in real space the autocorrelation of the Blur-Kernel. Okay, we could see those. That should have appeared. Anyway, here we see the power spectrum of the whitened image. So it's I convolved with D. This is the autocorrelation in real space. What we see here is the that guy up here. So this is whitening the image with the Laplacian, and this is the autocorrelation that we get in space. So some people have the impression that every differentiation filter is supposed to whiten natural image, but it's not the case. I think that you should be able to agree that this is more constant than this is. It's not constant, although we expect it to be, and we'll talk about that too, but it's more constant than this. I mean, this is, both these images, they seem to decrease as we go to the origin. So there was a work by Hu et al. That actually whitened the spectrum of the image using the Laplacian rather than the square root of the Laplacian, and they had very severe biases in the recovery of the Blur-Kernel.
This is a sort of spectrum. This is for a generic image. This is what you're showing.
It's the transform. It's a power spectrum of some image. Yes, some natural image. There are actually two of them. We'll work with them. Yeah, we'll see them. But yeah, I should have shown the images. By the way, in one-dimensional space, so if you assume that the blur is one-dimensional, you can basically do the same, but the differentiation can be done along that particular direction. So you could scan all the directions and check in which dimension the image seems to be most blurry, take that direction, and now use a differentiation filter to deblur the image. And actually, so a previous work by Itzhaki, they actually used the correct filter. So it was a first order differentiation, and they should have received a more correct whitening, although there is this issue of that phase recovery is harder for 1D signals than 2D signals. It's not unique. In 2D, it's thought to be unique. It has to do with the decomposition of multivariate polynomials, and there are some open questions in algebra, but the assumption is that it's unique in 2D and not unique in 1D. I mean, that could be shown. Okay, so as we've seen, there is a but here. This model predicts an isotropic behavior in the power spectrum of natural images, right? There's no dependence on the angle. But we know that the edge content in the images do influence the power spectrum of images. So those are the two images that we've seen earlier. These are the power spectra of these images, the non-whitened ones. And we see that these functions are very far from being isotropic.
Sorry, just
Yes.
how accurate is this exponent of 2? Like if you take 1,000,000 images, calculate the power spectrum, is it really?
So, well, maybe on a large ensemble, well, I don't know if in man-made scenes you would always expect to see these vertical and horizontal ones, so
Yeah.
I would expect some biases even in large ensembles. But we don't have that privilege anyway, so what we did is came up with a more refined power law, and the idea was to kind of look at the profile of these functions at various orientations, okay? And this is what we get on a log scale. And we see that we're actually getting these linear functions, and they just seems to be shifted by constant, meaning that there is some multiplicative factor that is different along each direction. So, which explains why, well, I'm sorry, why this model was kind of used so frequently. So there's some small deviation from that. And we use this model of the power spectrum of natural images to model for recovery of the Blur-Kernel. So we assume that there is some scalar C that depends on the angle theta here, which we can recover by the coordinates of the Fourier mode, right? It's the inverse tangents. Okay, so given that observation, we might need this tool, so let's look at it. The Fourier slice theorem gives us this relation. It's a relation between the transform Fourier of a projection of a 2D signal into 1D line with a line in Fourier space. So what we have here is we pick some direction and we project the image just by integrating along this direction. This gives us a 1D signal. Now we compute the transform Fourier of this 1D signal that was integrated along this direction defined by theta. And the identity tells us that this equals to a slice, just these values in Fourier space. Okay? This can be derived by thinking about the projection or the integration step just as if we're convolving the image with the function that is a delta function on one axis and a constant function on another axis, and then we're looking only one of the 1D line in Fourier space because the others are just constant, so there's no content there, and this is what we get. Okay, so what we have here is a parameterization of a line in a Fourier space. The orientation vector is r theta, and this is a scalar. Okay, so omega is two-dimensional coordinate in Fourier space, and xi is a one-dimensional coordinate in Fourier space. So applying this relation gives us the following final relation. So this is the Wiener-Khinchin relation, and now we have this relation, the Fourier slice theorem. So at the end of the day, we have a relation between the transform Fourier of the autocorrelation of a function after the image is being projected to a generic behavior in Fourier space, and we're kind of decoupling the C of theta variables this way. So let's just apply the same relation over, rather than the image, the blurry image, and we get basically this relation that if we take the image, we convolve it with this we first project it to 1D along some angle, we differentiate it in 1D, we compute the autocorrelation, and then go to Fourier space, then we are getting a slice of the power spectrum in Fourier space times some unknown constant. But those constants are decoupled from one another. I'm working with different projections, orientations, and in each one I'm getting this unique number C of theta that I do not know, and I'll have to recover. This have a real space counterpart. So here we're just projecting the image, whitening it, computing the autocorrelation, and we are expecting to see the projected kernel, its autocorrelation times some scalar. Okay. So the algorithm. So how do we use these relations to recover the Blur-Kernel? So I guess you can guess it by the relations that we've seen. So we take the image, we project it, whiten it, compute the autocorrelation to obtain these functions f of theta. So for each direction orientation, we have f of theta. So f of theta gives us almost what we need, which is the autocorrelation of the Blur-Kernel along one direction, or the projected one, or a slice in Fourier space. But there are two numbers that we do not know. So there is the C of theta that we don't know, and we've discussed it. And there's also another quantity, which is a scalar, an additive scalar that we do not know. And that results from the fact that this is a differentiation filter. So it loses the DC information of the signal, and that remains to be the case also in the autocorrelation of a function. So there is this uncertainty between f of theta and the true autocorrelation of that function. Okay, so to account for these, we have some physical priors over the kernel. One thing is that we expect the Blur-Kernel to be positive value, that it have a limited support, so it's not infinite, and we can bound it, and we actually assume that the user is giving us a bound, and that it has a constant sum. We can assume that it sums to 1. So we show that one can reduce both these unknowns and the constant sum to a different unknown, which describes the extent of the support of the kernel in each direction. Okay? Because if I know the extent of the kernel, and I know that by that time the kernel should be at 0, I know to offset it and recover m of theta. Okay? And I know that it needs to sum to 1, so I know to recover C of theta. So if I get f of theta, and I have these two unknowns, plus this assumption, given the extents of the kernel, I'm supposed to obtain, both m of theta and C of theta. So the algorithm basically recovers the Blur-Kernel and its extent and its support. These are the three variables. And it does that from the f of thetas that we compute. So we get the image. We start projecting it at different orientations. I will summarize that. We differentiate in 1D. We compute the one-dimensional autocorrelation. And we get these f of theta functions for every theta. Now we are recovering. So this is done once. Okay? And now we're recovering the Blur-Kernel and its support, basically, iteratively, using the following iteration. But this iteration is done only at the scale of the Blur-Kernel, not at the dimension of the image. The dimension of the image only affected the computation of these one-dimensional functions. So we start with some initial guess over S of theta, some conservative initial guess, which is the point where it shows minimal value, the autocorrelation that we computed, basically f of theta. And we estimate the kernel using the assumed support variables. So we get f of theta, and as we said, we can recover c of theta and m of theta and obtain the power spectrum of the kernel. And now we can use some phase retrieval algorithm, I'll talk about a little about it, to recover k, okay? And then we, given k, we re-estimate the extents of the support of the kernel along each orientation by computing the autocorrelation, projecting and computing the autocorrelation, and considering a point where the autocorrelation has decayed enough, and we repeat these steps iteratively. So here we can see an example. So we start with some initial guess over the support of the kernel. So this is the theta, the angle, and this is the extent of the kernel that we start with. And we start these iterations, step 1, step 2, and we are recovering both the kernel and we are converging to the true support, which is blue. So this is an actual synthetic example where we've blurred the image with the kernel, which we knew. So there's convergence both of the support and the kernel itself. And apparently, phase retrieval algorithms really benefit the most restricted prediction that you have over the support of the kernel that you're trying to recover. So every point where you can say it should be 0, it's a great help for the phase retrieval algorithm to converge.
I was confused about you have the sum to 1 constraint.
Right.
Is it for all? I'm just confused. Is it for all angles?
All angles, yes.
What sum to 1 over all angles? The projection of the kernel over in any orientation?
Right. So the sum of the kernel, the two-dimensional kernel, if you assume that this is 1, you're basically assuming that the Fourier transform of the kernel in 0 is 1.
Okay, yeah.
Right? So the autocorrelation, which is the square root of 1, is 1. And also its projected versions. So, well, basically when you project a kernel in 1D, you maintain its sum, right? So it's as.
So what happens if it's multimodal in some direction?
It could be, and actually it's what you see. There's one mode here and another here.
No, so if you're along a direction and you have a
So you might have, yeah, large value in the kernel, right? Large value here, small, and another large value. Might be the case, there's no limitation here.
then the support
So
is just a large.
Yes. It would be, for example, here, one lobe, another lobe. I mean, there's no assumption of unimodality here. Yeah. So how do we recover phase? We have the kernel. So we can recover many kernels, k of phi. So all of them have the correct power spectrum. So given the power spectrum, we can recover all these kernels, and they only differ by their phase content, right? Well, there are infinite solutions, as we can see. Here is the parameterization of these. But so in one-dimensional space, one can show that there is a finite number of solutions when we include these constraints. And as I said, it's thought that in two-dimensional space and higher, there's only one unique solution. But the problem is that all the phase retrieval algorithms out there, they're not guaranteed to converge to that right solution. And apparently it's very jumpy topology, so they do converge to different solutions. So it's not the matter of uniqueness that is the issue, but the ability to converge to the right phase. That's typically, well, especially when you have noise and you can't measure, you never know when you're there or not. So the typical phase recovery that people use, it's an algorithm from the 70s, FinUp. It does very simple iteration. So we start with some given power spectrum. It's F, okay? And what we do, we start with some initial guess of the function in real space, the kernel in real space. We compute its Fourier transform. Now we correct the constraints in Fourier, which basically tells us to change its magnitudes to the given magnitudes, but we maintain the same phase. Then we go back to real space, and now we apply the spatial constraints, which are the positivity, limited support. We just start setting values to 0 and clump them below 1 if needed, or maintain some integration, and repeat this process again. This is a very old strategy, but it's still the state of the art. So let's summarize the algorithm. So I'm given with a blurry image. At first, I'm computing these f of theta functions. So I'm taking that image, I'm rotating it, projecting it by just summing the pixels along one direction. And then I am whitening it. So I'm differentiating it in one dimension and computing the autocorrelation. And we see these 1D functions stacked here. So this is the polar coordinate, and these are the slices. Okay. So each one of them is multiplied by some arbitrary c of theta that I need to recover, and there's also the missing additive m of theta. This is why we see these discontinuities and so on, right? And now comes the iterative phase, where we're trying to estimate m of theta and c of theta, but we're doing it actually indirectly through the s of theta, the extents of the Blur-Kernel that we're updating. And what we're doing here is the following iteration, basically. So this is the iteration. So we're assuming that we know the extents of the kernel. It's not m of theta and c of theta, it's s of theta, the extents. And given those, we normalize each of these one-dimensional functions, right? If we assume that we have s of theta, we know m of theta and c of theta, so we could normalize them. This is a converged image, so it looks much nicer than this. So this image differs from this by just multiplying by a scalar and some additive scalar of each of the rows here. Each line here corresponds to some slice in Fourier space, which we just copy. And these are the power spectrum of, gives us just a power spectrum of the Blur-Kernel. Now we use a phase retrieval, an iterative phase retrieval to recover the kernel. From this kernel, we start estimating s of theta, the compactness, the size of the kernel along each direction. We go back, we renormalize, and do this repeatedly, okay, until we converge. So one note about the noise. We assumed that in the original Blur model, we have the convolution plus additive noise. So the noise is actually being reduced by this projection operation, because we have independent noise in each pixel, and by transferring from the blurry image into these f of theta image functions, we're integrating along one direction of the image. We have n pixels. If we have n pixels, then we're reducing the noise by 1 over square root of n. Okay, let's see some sets.
So now that you have an estimate of the image, is there any value to say
of the kernel?
What? Well, both, right? Kernel and the image.
So in this process, we never recover the image.
Okay, well, but you can't. I mean, okay, so fine, all right.
Right, but I can use some non-blind deconvolution to recover the image. Sure.
Right. Okay, so sorry.
It doesn't help me. Yes.
Okay, but you could do that.
Right.
And then you could get a much more accurate estimate of the power spectrum of the image. And then you could repeat the whole process by modifying your whitening. Would there be any value in that?
You mean C of theta?
Not necessarily. Maybe it's not exactly a power law. Maybe it's something, slightly different. But you could actually measure what it was. And then you could go through your whole process again.
Right. We never tried that. We never tried that. Well, the most immediate thing that I think is just actually recovering C of theta. That sounds like the immediate thing I would have tried. No, we haven't tried that. It's, yeah, interesting. But we were actually in this mind setting where we said, okay, no playing with the image. Okay, we want to go from this high-dimensional image to this tiny kernel, just work here as much as we can, and that's it. So
what do you do about the boundaries of the image? Because each projection has a slightly different size and, Fourier transform
True.
square cyclic graph domains.
Right. So that is basically the reason why we haven't, I kept on mentioning the spatial counterparts. I didn't really need them. I could have done everything in Fourier space. But the problem is that, sure, the image is not cyclic. So in Fourier, I would start seeing these biases. And so that's what made us compute the autocorrelations in real space. Well, there are a lot of very reasonable ways of dealing with the boundaries. So what you're saying is that the autocorrelation I can compute here is very wide, is actually narrow, and as I'm rotating, I have a larger one. But the thing is that we need f of theta just at the size of 2 times the width of the Blur-Kernel. So we just don't have that problem. Okay, so. Okay, so input image, output. If we can dim the light, or we don't do it because of the recording, right?
It's okay. When you say dim the light, the person in the back does this.
I see. Okay. So input image, output image. The blink is supposed to blind you. Input image, output image. Comparison with other methods. Input, our output.
I'm confused. Why do you do the blinding? What do you?
I did not prepare these slides, and I forgot to remove it. I know it's very annoying. It's my student, here's a comparison again with other methods. So I think that in terms of quality, we're kind of meeting the state of the art, which is somewhere between Levine and Schoenli. Input, output, comparison. Input, output. It should be comparison of that, input, output. So the nice thing is that this power law, 1 over omega squared, is actually the result of the presence of step edges in the image. I mean, you could do this exercise, just take a Heaviside function, compute its Fourier transform, see that it's 1 over omega, and the square root of that would be 1 over omega squared. The thing is that apparently also clutter also gives this spectrum, and it gives this spectrum from even smaller chunks of the image. So the methods, we have this advantage over methods that search for well-resolved edges and do this local fitting and so on, where clutter actually reveals the, for us, I mean, it gives the whitening, the property of 1 over omega squared, which you can use for whitening and recover the Blur-Kernel. So very cluttered images of deserts or foliage is actually playing into our hands. So output.
Can you use a small enough spatial support that you can get a nicely spatially adaptive kernel estimate?
I think we played it that just a bit. So if the image is large enough, we could just run the algorithm here, 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 and recover these different blur kernels. But now you need some generalization of this model for the entire image. But at this point, we decided that, OK, why should we do it with our algorithm? I mean, many algorithms can be applied at different points in space and then recover the 3-dimensional blur kernel somehow. But it's an interesting direction. I don't think I've seen someone doing it, so it's kind of surprising. Yes.
That's not harsh at all.
But do they? I mean, I don't remember the details. What Bill was suggesting is apply a translation invariant algorithm in this part, in this part, in this part. Just sample them, so you get different 2-dimensional blur kernels. Now you have to search for the 3-dimensional blur kernels, such that if you would kind of like project it. So it's not what they've been doing. They've been working with a 3D.
From rotation, you're assuming everything's from translation now, so it's invariant, but if you sort of added a rotation,
Exactly,
let's say
yes.
around the center, for example.
Yeah.
could
Yeah,
you-
this
could
is
you
what
then
I'm calling-
extend one more dimension, maybe?
Right. So this is what I'm calling the three-dimensional Blur-Kernel.
Yeah.
It has another axis of rotation, and then given a few two-dimensional Blur-Kernels, could you estimate the three-dimensional? It's an interesting question.
We have an ECC paper, and Joseph Civic and Oliver White have a similar paper, CVPR, that really do that. They take these 2D estimates as a bootstrap for trying to estimate that.
I see.
So better localized 2D estimates would be helpful.
Right. Okay. But that was in some global optimization over the three-dimensional kernel.
Yes.
Yes. Okay, some numbers. So we compute, these numbers are for a 1 megapixel image, blurry image. So it takes us about 2 seconds to compute all the f of theta. I mean, project the image onto the different orientations. Then 12 seconds we spent on the phase retrieval thing and the outer iteration. Lots of iterations there. We are actually starting with 30 initial guesses for the phase retrieval. So phase retrieval is an issue. Nevertheless, this is supposed to scale with the blur kernel size, and this is supposed to scale with the image size. So it could be cases where it might be better or worse. Both of them are really trivially to parallelize because projecting the image onto different directions can be done in different CPUs. And the phase retrieval, when you start from different initial guess and just start iterating, it's just this genetic optimization algorithm which can be done on multiple processors. We ran also the quantitative comparison. So we used 8 images of a data set of 8 images for nature images, for man-made images. It's not the images, and we use 9 kernels from the data set that Levine built. We did not use her images because her images are 256 by 256 pixels, which is too small for our algorithm to work because our algorithm kind of estimates statistics, basically, right? So the smallest images on which we've been enough successful were 512 squared. Okay, so her data set was just too small for us. And then we used her metric, which is actually asking what is the deconvolved image that you get from your kernel minus the true sharp image versus the deconvolved image that you get from the true kernel minus the true image. And
which deconvolution technique?
We used Dilip's hyperlaplacians, yeah. And then we look at the function of the images that is below epsilon, if I remember correctly. So this is what we obtained. So those are images you're not familiar with. We used them, but we did use the same blur, the blur patterns that are not used. And these are the result that we get. So we're in par with most of the state of the art in respect of this measure. Dilip, you're not doing that great here, but okay. One failure case is, so what happens when we have a repetitive pattern in the input image itself, intrinsically? So this image is kind of similar to itself in the short version of it, right? So here's a blurry image. This is our result. It's very ringy. So I don't have the sharp version of this image, right, because I just found it on the web. But I did search for another sharp image of the same bridge, okay? And I computed the autocorrelation of that function. So that should have been a delta function. And look what we get. We get something that is different from, just because we have these periods, consistent periods, right? It's these distances that if you move, you get a peak in the autocorrelation function. By the way, if they were large enough and the Blur-Kernel was smaller, then we might have a small region in which it was sufficient for us to recover the Blur-Kernel. But in this case, it's relatively small, and this is a classic scenario where we cannot expect our method to work.
Is your orientation, the kernel orientation, if you sample the orientation really, really densely, then can you deconvolute that image as well? Because
no. won't help me to cope with this. I mean,
Because each line has a little bit different angle.
right, but still at that particular, I mean, well, I think that the autocorrelation that, so this is supposed to give me an autocorrelation along this direction, right? If I move the image in this direction, I'm supposed to see these additional peaks. But I think that even if I move a little bit in the orientation, I would still see, so it's not like a matter of high precision, like the correlation that you see is substantial. I think it's not very fine lines. That's my guess. But unless if the image is huge, but yeah, I don't think in practice that would help much.
Sorry to ask
Yeah.
a silly question, but what assumption is it about the image that says that it's whitened out of correlation function, which would be a delta function? I mean, I guess it's just the spectrum. Okay.
Yes. So if you think about derivative images, so you have these peaks somewhere, right? Now we want to say that statistically, if I saw a peak, which was basically an edge, there's no fixed distance that I would move, and on that particular fixed distance, I would see another edge. Right? So we have edges in images, but just two edges, they're not always, there's no reason for two edges to be always at this particular distance from one another. But here it happens.
Can one just ignore that direction and compute it on the kernel?
Yeah, so I might have hole in the kernel, right? So, but then again, I don't know how to do it a priori because I don't know that was I mean, I don't know if it was the Blur-Kernel that did it. I don't know if it's the real image. That's this major ambiguity that even if you would tell me this direction is bad, then maybe I could do something, but I could not do it. It might be the result of the Blur-Kernel. Like a weird Blur-Kernel that have delta, 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 it could produce this.
Yeah, I mean, not looking at the whole image, but just looking at 6 of these stripes, it could have been one wire with the Blur-Kernel that was just a very stuttered kind of thing.
Exactly.
So it's interesting that like the tree regions don't seem to have that problem because they're sort of
they're very similar in your
periodic,
eyes.
but maybe not as strictly periodic.
Yes, but they don't have, I mean, they might have dominant scales, but they have enough variation around that. Yeah, I know, it's kind of surprising. You might think that there's a very particular scale that would play here, right? But if you look here, it's kind of different than here, and then you're integrating across the entire image, and then there's here, so somehow yeah. So let me summarize. So it's easily parallelized, the algorithm. Image size affects only one component of the image, the projection step. So the larger the image is, the lower the noise is, but I'm guessing that many other algorithms would enjoy that. So we're not repeatedly recovering the latent image as the map algorithms do, and therefore we're much faster than them. And we are not relying on our ability to detect the specific edges. So, for example, a multimodal blur that Dilip mentioned, it's always hard to say where was the edge. So we don't have that issue. But then this model and all the Fourier transforms that we've been using so much requires the algorithm to, the model to be like the convolution blur. And also we cannot operate on small images just because the statistics are not converged, and definitely not spatially varying blur. That's out of the question. Okay, that's it. Thank you. Questions?
Sorry,
Yes.
stuck on the image of the Zayton Bridge. So suppose you ran it through your algorithm, the one on the far right. You get some Blur-Kernel that would be a more succinct explanation of that image. You could find some latent Zayton Bridge image that didn't have the repeated guy. I don't know.
That's what the middle image is, right? Sort of. It basically hallucinates repetitions.
This is the whitened one. Yeah.
The middle image is the result of your technique,
Yes.
right? So what it does is it hallucinates repetitive structure here in order to make these things sharper, right? So, or maybe not sharper, but somehow more statistically white. Right?
Yeah.
Exactly. So if I would differentiate this image and look at the autocorrelation, that would be white.
Yeah.
So this image has a much higher total variation probably.
Right.
So if one tried to minimize that, then
Now it's a fight between a very wrong kernel and then the natural image prior that would. And actually, this algorithm for recovery, it has that, right?
then is it a property of this image or this image in the algorithm? Like would other, I'm trying to think, would other deep learning, other kernel estimation algorithms, would this be a puzzler for them too, or would they find it?
Depends how many checks and balances you put in, right? Like for example, the edge-based techniques, which I'm most familiar
They
with.
won't suffer from it.
As long as it, if it found the top edges of the pylon and focused on that, it would get the right thing. If it happened to zoom in on the strings and the search area was big enough that it actually found the string, it would be very convinced from that. But of course, if you put in enough checks and balances and saying it's just an isolated thing on this image region, if you had some sort of a ransack-like thing, that maybe said sometimes there is real repetition, so we'll do that. In other words, more you look at regions where there is a single step edge and nothing else. Because one of the things that struck me looking at your earlier examples is like our technique would have a harder time with the tulip, where the white tulip is over the background of a very green textured thing, right? Because it really assumes a local two-color thing, right? Here, luckily, the sky and the pylon is very good. Right? But there, where there was that faint little echo of a white tulip against some green textured leaves, our technique would be struggling, right? Yeah, no, there's no free lunch. The best thing you can do is hope that there's a glitch somewhere. And then,
that still isn't even that easy, right? Because your glit's usually saturated, so.
Yes,
Right.
that's right.
That's it.
The glit's at different intensities.
Yes.
Okay, thank you.
Okay, thank you.